Hello students, welcome back. So we have seen how binary, decimal and hexadecimal numbers can be represented. Now we will look at how signed numbers can be represented. That is, we want to represent both positive and negative numbers. First of all, if we have unsigned binary numbers and we have n bits, we can have each of the bit can have 0 and or 1. And we have seen that using n bits, we have discussed that we can represent the numbers from 0 to 2 to the power n minus 1. Now we want to look at suppose we have 3 bits, then we have 8 distinct combinations. So for n equal to 8, if there are 8 bits, that's 1 byte, we can represent 256, 2 to the power 8, 256 different numbers ranging from 0 to 2 to the power 8 minus 1. But what if we want to also represent negative numbers like minus 7, minus 20, minus 512? So then we have to come up with a signed representation. Now there are various ways in which you can think of representing signed numbers. We will discuss 3 possible approaches and then we will focus on the approach which is most commonly used, which is the 2's-complement representation. But first we will discuss the sign magnitude representation and the 1's-complement representation. What is the sign magnitude representation? It's a very simple to think about. If you have n bits to represent a number, you can reserve the leftmost bit for storing the sign. We can say if the leftmost bit is 0, then the number is positive. If it is 1, the number is negative. So this bit represents the sign and the rest of the numbers, n minus 1 bit represents the magnitude. So in this case, suppose we have 4 bits, then these are the numbers whose leftmost bit is 0. These are the numbers whose leftmost bits is 1. So these are all the positive numbers and these are all the negative numbers. And then if we look at the right 3 bits, they represent the magnitude. So this is plus 0, plus 1, plus 2 up to plus 7. And this is minus 0, minus 1 up to minus 7. So what do you notice? 15 distinct numbers can be represented. There are 2 representations of 0, plus 0 and minus 0. Of course, plus 0 and minus 0 are equivalent. So 15 distinct numbers can be represented. 7 positive numbers, 7 negative numbers, and 0. And what is the largest positive number that can be represented? So because we are using 1 bit for the sign and n minus 1 bits for the magnitude, the largest magnitude is 2 to the power n plus 1 minus 1. So the maximum, the highest positive number is plus 2 to the power n minus 1 minus 1. And the smallest negative number is the negative number with the largest magnitude, that's the smallest negative number, is minus of this. Okay. So there is one problem, of course, that there are 2 representations of 3. Next, we look at the 1's-complement representation. So positive numbers are the same as in sign magnitude form. For negative numbers, we represent those numbers in 1's-complement form. What is 1's-complement form? If we have a number, let us say 1, 1, 0, 1, 0, 0. To find the 1's-complement, we will reverse, we find the complement of each bit. So this becomes 1, this is 1, this is 0, this is 1, this is 0, this is 0. Okay. So to find the 1's-complement of a number, we must complement every bit. That is, 1 will become 0 and 0 will become 1. And then the MSB will represent the sign of the number. If the MSB is 0, that means the number is positive. If the MSB is 1, the number is negative. So let us look at ones complement representation. These numbers whose MSB is 0 are positive numbers. They are represented as it is, 0, 0, 0, 0, 0 and 0, 1, 1, 1 is 7. And for negative numbers, we represent it as ones complement form. So suppose we want to represent minus 7. So minus 7, the plus 7 is represented as 0, 1, 1, 1. And therefore, minus 7 will be represented as 1, 0, 0. Similarly, plus 4 is represented as 0, 1, 0, 0. And minus 4 is the complement of it is 1, 0, 1, 1. So these are the ones complement which represent the negative numbers. So as I already told, to find the representation of minus 4, first you write the representation of plus 4 and complement the bits. So if you complement the bits, the negative number, its MSB will become 1. Because in the original representation of the positive number, the MSB is 0. When you complement it, it becomes 1. So if you use the ones complement notation, the maximum number, positive number that you can represent. Here also you see that there are two representations of 0. And we see that the maximum positive number, largest positive number is plus 2 to prime minus 1 minus 1. And the smallest number is minus of 2 to prime minus 1. Two representations of 0. But ones complement representation has some advantage. It can be shown that we can perform subtraction by using only addition. This helps us in using the same circuitry for addition and subtraction in the arithmetic logic unit of the computer. The second advantage is that sign extension is possible to increase the number of bits to represent. For example, suppose we have represented minus 3 in 4 bits and the representation is 1, 1, 0, 0. Now, if you want to represent it in 8 bits or 16 bits, you can take the rightmost bit and you can repeat it. And then you will get the representation of the number in 8 bits. Similarly, if you want to represent minus 4 in minus 3 in 16 bits, you will add more ones to the left. And this is one advantage of ones complement. We will not talk into the details of ones complement, rather we will focus on the twos complement representation, which is the one which is most popular and used in modern computers. The basic idea of twos complement representation is that first of all, positive numbers are the same as in sign magnitude form. The MSB is 0 and the rest of the number gives the magnitude. Negative numbers are represented in twos complement form. What is the twos complement? We take a number, suppose we want to represent minus 7. We take the number 7, we complement the bits and then add 1. So this gives us the twos complement of the number, and MSB will indicate the sign of the number. 0 is positive, 1 is negative. We'll take an example. So for n equal to 4, the positive numbers are same as we have seen before. For the negative numbers, let's see how to represent minus 4. So first we take plus 4, which is 0, 1, 0, 1. The ones complement is 1, 0, 1, 1. And we add 1 to get 1, 1, 0, 0. So 1, 1, 0, 0 is the representation of minus 4 in twos complement. Okay. So the twos complement of a number we get by complementing the bits and then adding 1. So if you use a twos complement representation, what you notice is that there is only one representation of 0. There is one more negative number than positive numbers. And the maximum positive number is plus 2 to the power minus 1 minus 1. and the smallest number is minus 2 to the power n minus. So 2's complement number has certain advantages. There's a unique representation of 0. Subtraction can be done using addition. This leads to substantial saving in circuitry, and you can also do sign extension. So if minus 3 is 1101 in 4 bits, you can take the MSB and you can repeat it to get this number minus 3 in 8 bits. So plus 30011, if you want to represent it in 8 bits, you take the 0 and repeat it. Almost all computers today use the 2's complement representation for storing negative numbers. So in your C compiler, the most C compilers, the typical values are, it can vary from compiler to compiler, but typically short int is 2 bytes, that's 16 bits, and it can store numbers whose largest number 2 to the power 15 minus 1 and the smallest number minus 2 to the power 15. Int is 32 bits, which can store the largest number is plus 2 to the power 31 minus 1 and the smallest number is minus 2 to the power 31. Long int uses 64 bits. The largest number is plus 2 to the power 63 minus 1 and the smallest number is minus 2 to the power 63. Okay. So is this clear? So how to get a 2's complement? Why do we call the 2's complement? Suppose you take the number, what is the 1's complement? Suppose you have a number 1011. What is the 1's complement? 1's complement is subtracting the number from 1111. If you subtract the number from 1111, what you get is 0010. You get the complement of the bits. What is 2's complement? Is adding 1 to it. That is, it is, suppose you have this number 1011. If you want to find the 2's complement, it is same as subtracting it from 1 and 4 zeros. So if you have n bit number here, so you are subtracting it from 2 to the power n. So 2 to the power n minus x is the 2's complement of x. Okay. And what is 1's? So this is 2's complement of x. Now, based on this understanding, we will look at how addition is performed on binary numbers and how subtraction is performed. First, let's look at binary addition. You all know addition, and you know when you add two numbers, you write them so that they are aligned. And then you start from the right and keep adding the digits of the two numbers and you have a carry. And so these are the rules. So if you have only binary numbers, the bits are 0 and 1. So there are 4 possibilities: 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1. And these are the results. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 0 is 1, 0. Out of which 0 is what you put in this position and 1 is the carry. So if you are adding these numbers 0, 1, 1, 1 and 0, 0, 1, 1, 1, 1, this is 0 is the result, 1 is the carry, 1, 1, 1, 1 is the result, 1 is the carry, 1, 1, 0 is the 1, 1 carry. Okay. Now consider this set of numbers 1, 0, 0, 1 plus 1, 0, 1, 0. If you add, here you get 1, here you get 1, here you get 0, here you get 0, and there's a carry of 1. So you have 4-bit numbers. When you add, you may get a 5-bit number that this one is the carry. This is the carry out of the number. Now let's see how we can perform subtraction using addition. Before we come to the 2's complement representation, let's look at how subtraction is done for 1's complement representation. Suppose we want to compute a minus b, we will first compute the 1's complement of b, that is b1. And what is b1? It is nothing but, if you are using n bits to represent the number, b1 is 2 to the power minus 1 minus b. This is the definition of 1's complement. So now we will compute R equal to A plus B1. What is A plus B1? It is actually 2 to the power n minus 1 plus A minus B. So if this number is positive, 2 to the power n minus 1 plus A minus B, then after we do the addition, the carry out will be 1 and the rest of the number we get is A minus B. So if the carry obtained after addition is 1, then we get the actual number and we can add the carry, this carry back to the result. R, this is called the end around carry. That is R equal to R plus 1 plus 1. So this one we will add. So we get 2 to the power n plus A minus B. This 2 to the power n is the carry. And the result is a positive number. But if there is no carry, then what we get is we will get the ones complement of B minus A. So this 2 to the power n minus 1 plus A minus B is the ones complement of B minus A. So if A minus B is negative, B minus A is positive, and the ones complement is what we get. So the result, if the carry out is 0, the result is negative and is in ones complement form. So let's take an example. We want to compute 6 minus 2. So 6 is represented as 0, 1, 1, 0. And 2, minus 2, if you want to get, first let's get 2. What is 2? 2 is 0, 0, 1, 0. What is minus 2? We will get the ones complement as 1, 1, 0, 1. So 1, 1, 0, 1 is B1. Now we add A plus B1, we get 1, 0, 0, 1, 1. This 1 is the carry. So we will add this carry to the number to get 0, 1, 0, 0. And this is the result. This is a positive number, which is the result of 6 minus 2. Now let's take another example, 3 minus 5, whose result is negative. So this is the number 3, and this is the ones complement of 5. What is 5? 5 is 0, 1, 0, 1, and this ones complement is 1, 0, 1, 0. So put 1, 0, 1, 0. When we add, we get 1, 1, 0, 1. So carry out is 0. So we can say that this is a negative number and its ones complement gives us the magnitude of the corresponding positive number. What is the ones complement? It is 0, 0, 1, 0, that is plus 2. And therefore this number is minus 2. Now let's move on to 2's complement, which is more important. How do you compute A minus B? So first we will take the 2's complement of B, that is B2. So R equal to A plus B2. And we have seen that B2 is nothing but 2 to the power n minus B. Now, if the carry obtained after addition is 1, we ignore the carry, the result is a positive number. No end around carries. So if the carry, so if we do A minus B, we do A plus B2. So we get A plus 2 to the power n minus B. That is 2 to the power n plus 1 minus B plus A minus B. What is 2 to the power n? It is 1 and then n 0. So this A minus B will be the rest of the bits and there will be 1 at the outside. So if we ignore this number, we will get, if we ignore 2 to the power n, we get A minus B. Otherwise, if there is no carry out, the number is negative and it is in the 2's complement form because it is 2 to the power n minus B minus 2 to the power n plus A minus B is 2 to the power n minus B minus A. So this is B minus A in negative of B minus A. So the result is negative and this is 2's complement form. So let's take the same example again, 6 minus 2. 6 is represented as 0, 1, 1, 0. 2 is represented as 0010 and its 2's complement. We first complement the bits to get 1101, add 1 to get 1110. So this is B2. When we add A and B2, we get 10100. This 1 is the carry, and therefore this is a positive number, and we get this magnitude here. If we do 3 minus 5, 30011 as usual. 5 in 2's complement form is, first we invert the bits of 0101, add 1, we get 1011. When we add them, we get 1110. The carry is 0, therefore this is a negative number, and we can find the magnitude by taking the 2's complement. The 2's complement is 0001 plus 1, which is 0010, that is 2. Therefore, this number represents minus 2. Okay, is this clear?